Okay, this is a video is going to be a brief explanation of gas law stoichiometry. And the good news is for this gas law stoichiometry stuff is we're really only doing one new step compared to the stoichiometry we've done in the past. And that new step is translating between the volume of gas and its number of moles. And then the rest of these problems is just doing the same thing we've been doing for stoichiometry, which is converting moles of one substance to moles of another, and then getting those moles into whatever other form we might like, be it grams, or now in this case, maybe it's liters. So let's take a look at an example. This video is kind of a guide to the homework on let's see, it's CV 12.2. And so I'm going to use some of the same equations, and we're going to set up some similar problems, so you should be able to just kind of walk through some of the homework if you're struggling. Okay, so here I'm going to take a look first at the combination of solid sodium with some gaseous chlorine to form some solid sodium chloride. And I'm going to take a look at a question that says, at STP, what volume of chlorine is required to react with, let's say, 3.45 grams of sodium. So we're given this kind of starting condition. Okay, we'll always be given a temperature and a pressure, and then we'll be given some other parameter, something that'll allow us to do the stoichiometry. In this particular case, the temperature and the pressure are given to us right here at STP. And STP stands for standard temperature and pressure, and it is 1 atmosphere of pressure. It could also be 760 millimeters of mercury or 760 torr. It could also be 14.7 psi. Any of those kind of those pressures in any of those labels on that big equivalency are all standard pressures, so you can use whichever one has the label you need. In this case, though, we're going to use atmospheres. Atmospheres are going to be our usually the one we want to have. They're going to be the most useful for the ideal gas law if we choose to use the ideal gas law to solve this problem. There are two ways, and I'm going to show both. Okay. So anyway, STP is 1 atmosphere, and the temperature is 0 degrees Celsius, which is nice and easy to remember. But more relevantly to us, it's 273 Kelvin. And why that's more relevant is that for any gas law problem at all, you need to use Kelvin. And so we might as well just write the STP down as Kelvin. That way we can plug and chug into our formula when we get to that point. Okay. So now, as I said earlier, the only new step in this gas law stoichiometry is kind of going from moles to volume. And so in this problem, the new learning is going to be saying, taking the step of moles of chlorine to volume of chlorine. Well, in order to take that new step, we need to have the moles of chlorine. So our first goal is to be determining the number of moles of chlorine necessary. And the good news, for you ladies and gentlemen who kind of have, hopefully kept up with the class, is that this is going to be done exactly the same it was in our previous chapter, in chapter number 9, when we focused on stoichiometry. This is now the exact same sort of problem. So what we're going to start out with is this 3.45 grams of sodium, and what we want to end up with are some moles of chlorine gas. Okay. And so to get there, first off, in order to change substances, we have to be in moles. And so I have to turn these grams of sodium into moles of sodium. And I have 23 grams to 1 mole for sodium. That comes off the periodic table. And then I need to get rid of those moles of sodium. So I'm going to put those in the bottom. And I want to end up with, oops, I shouldn't have written a 1 there. It's not a 1. And I want to end up with some moles of chlorine gas. And then that'll allow me, that'll transfer my label to moles of chlorine gas, and it'll give me this answer that I'm looking for. In this case, I go back to the balanced chemical equation and I say, well, there's 2 moles of sodium for every 1 mole of chlorine. So there are 2 moles of sodium for every 1 mole of chlorine. Now I'm ready to solve this kind of setup of the problem. And so we're going to need some 0.075 moles of chlorine. That should all be kind of review. I know maybe it's been a while since we've done it, and especially in the current circumstances, things are probably a little bit more difficult to keep organized. But that is all, at least all learning we should be somewhat comfortable with by this point. And now for the new step, we're going to determine the volume of this chlorine gas. And for us, this is going to be really easy. I'm going to do it both ways, one of which is going to be substantially harder than the other. But I want you to get it in your head that you can solve these either way and in conditions that aren't at STP, like in the next problem. It's totally your decision. Both ways are about as difficult as each other, so it's just which one you feel more comfortable with personally. So first, to determine the volume of chlorine, I am going to use, I'll do the easy way first. I'm going to use the fact that at STP, any gas, it has a volume of 22.4 liters per 1 mole. And so as long as we're at STP, we can just apply this conversion factor to our number of moles. It'll give us our number of liters, and we're done. So in this particular case, since we are at STP, that is by far the easiest way to do this. And I'm just going to say times that 0.075 moles. And again, this works for any gas. Doesn't matter what the gas identity is, only matters how many moles of it there are. And we would find out that we'd have some 1.68 liters of chlorine gas needed. Okay. Now in problems that aren't at STP, we can still use this conversion factor to find out what the volume would be at STP, and then use the combined gas law to translate that volume to what the volume is at the actual set of conditions. I'm going to show an example of that with the next problem, but before I move on, I want to show that this problem can also be solved by the ideal gas law. And the ideal gas law, again, is PV equals nRT, where R is 0.0821 liter atmospheres per moles Kelvin. And that is just a constant. P is pressure, V is volume, N is the number of moles, and T is the temperature in Kelvin. So let's go ahead and put those things into this equation, and it should give us out this same 1.68 liter volume. Okay, we said we had a pressure that was standard, so that's 1 atmosphere. We have the volume that we're looking for, so we're going to leave that just as a V. The number of moles that we had were 0.075. R is 0.0821. And at STP, the temperature is 273 K. And now if we just go ahead and multiply those three things together, we come up with this same 1.68 liters of chlorine gas that we should have. The universe is happy. These laws are consistent with each other. Okay, so what about if we have something that isn't at STP? Well, how can we handle that? Well, relatively easily. So let me just take a look at what I've got for a problem for the second one on the homework, and I'll give you a very similar one. Do I not have the homework open? Give me just 1 second. I apologize. I thought I had left that sitting open, but I did not. This is 12.2. Oh, not 12.2. Must be a 12.3. I thought it was 12.2. 12.3, I apologize. Okay. So for the second one, we had some combustion of propane. And we want to do some gas law stoichiometry with that. And so we'll say our set of conditions are at 25 degrees Celsius and let's say 1.25 atmospheres. Okay. And then we're going to take a look and let's say if we wanted to combust, the amount of oxygen required to combust. And let's say 65 grams of propane. Okay, so the first part of this problem is going to be the same thing as the first part of our other problem. Again, the only new learning here is that moles to volume relationship. So the first thing you're going to want to do is find out the moles of oxygen. And we're going to do so out of these grams of propane. Now, for the grams of propane, carbon's 12 on the periodic table. We have 3 of them, so that's 36. Another 8 for our hydrogens means that we have 44 grams per 1 mole of propane. That's a big 8. Okay, and then I want to change my substances, so I want to get rid of those moles of propane, and I want to move to my moles of oxygen. And then once I get that answer, I'm ready to do my new work with this either ideal gas law or combined gas law. So the only other thing I've got to do here is I don't know what factors go in here, so I have to come back to my original equation, and I see this is not balanced, and so I need to balance it. And so I can see right here that I'm going to try starting. I need to have some even number of waters. And so I'm going to take this H8 and I'm going to say, well, let's try a 4 there. That would give me 8 hydrogens. Gives me 4 oxygens. And here, if I try a 3 to get my carbon straightened out, I can see that, well, I've got 4 oxygens there. I've got another 6 oxygens needed there. And so I need 10 oxygen atoms or 5 diatomic pairs of oxygens. So now I've got this, all these coefficients into my balanced chemical equation, and I can fill out my mole ratio. I'm going to say 1 mole of propane, and up here I'm going to say there are 5 moles of oxygen. Now it's just running it through my calculator, and it'll tell me how many moles of oxygen I need. And I need some 7.4 moles of oxygen. Okay. And now we're down to our new bit of work where we're going to use these moles of oxygen and we're going to turn them into volume, into liters. And so I'm going to start off, I'll start off with the same way I did last time. I'm going to start off by using the combined gas law, along with that known fact that 22.4 liters of gas equals 1 mole at STP. So I can say at STP, this 7.4 moles of gas would be 22.4 liters per 1 mole. And that would give me that I've got some 166 liters. And then I can use the combined gas law to change this from the set of conditions that I have, or from STP to the set of conditions that I have. So combined gas law is P1V1 over T1 equals P2V2 over T2. And we're going to use this fact here. We've got one set of conditions, and so we're going to fill out this P1V1, and then we'll fill out and solve on the other side. So here at STP, I have a pressure of 1. I have a temperature of 273 K. Oops. So I've got a pressure of 1. I've got a temperature of 273, and my volume is this 166 liters. On this side, I've got a pressure 2, my new one, the one that was given in the problem, which is 1.25 atmospheres. I don't know my volume, so I'm going to leave that as a V. And my temperature 2 was at 25 degrees Celsius, add 273 to turn that into Kelvin, and we would find out that we're at 298 Kelvin. And now this is just simple algebra to solve for V. I'm going to take my 166 times 1 divided by 273, times it by 298, and divide it by 1.25. And I find out that my volume of gas under these conditions is 145 liters. Okay. So that's one way of solving this problem. That will work all the time using that 22.4 liter conversion, and then using the ideal gas law, or the combined gas law, excuse me, to convert that into whatever set of conditions you're given in the problem. The other way that works is using the ideal gas law, and once again, this should give us exactly the same answer. Yeah, but let's just go ahead and verify that indeed everything is true about the universe and that these things are all consistent. So we're going to say that ideal gas law, PV equals nRT. Here, our pressure given in the problem is 1.25. Our volume is what we're looking for. We have some number of moles, that's 7.4 moles of oxygen we needed. It's going to be multiplied by this constant 0.0821 for R, and then it's going to be at the temperature given in the problem, which is 298 K. And if we run that through our calculator and solve for V, we should come out with exactly the same thing we did. And indeed, we come out with this 145 liters. So again, the meat of this problem, I think what most of you struggle with is just this basic stoichiometry stuff to get it into the moles of gas. Once you have it in the moles of gas, and this becomes just another gas law problem. Checking in the homework that I've seen on the other assignments, we seemed much more comfortable with just applying those gas laws. So you might need to kind of brush up on your generalized stoichiometry skills. These are all going to be essentially the same thing. The next problem on this review is a limiting reactant problem, and I'm going to kind of leave that for you ladies and gentlemen to do. What you want to do is take the volume of the first gas, turn that into some number of moles. Take the volume of the second gas, turn that into some number of moles using either one of these two paths you want. I would think for that problem, ideal gas law will be a little easier. That's the approach I would take, but you can solve it either way. And then you'll have turned those into moles of these substances, and then this is, at that point, becomes just a normal stoichiometric limiting reactant problem. And if you need help with those, go ahead and review the video on, limiting reactants. Everything's still up in our class files, so If necessary, I'll make another video about it, and I might anyway, just because I know a number of you are struggling with this concept, which is very typical, even in the classroom. Anyway, I might make another video about stoichiometry, and if I do, I will post it onto the YouTube channel along with the rest of them. Hope you're having a great day, and I'll see you in the next video.